For over 2 decades, the Lambda-CDM model, with its static cosmological constant, has been cosmology's foundational pillar. It predicts an unchanging form of dark energy, represented by a perfectly flat line at W equals -1, leading to a universe destined for eternal runaway acceleration. But the Dark Energy Spectroscopic Instrument, DESI, has now measured the universe's expansion history with unprecedented precision, and it has found a compelling hint that this pillar might be cracking. The new DESI data, when combined with measurements from the cosmic microwave background and supernovae, reveals a preference for dark energy that is not constant but dynamic. The data shows a gentle curve, a hint that dark energy's repulsive strength may have been weakening over the last several billion years. Statistically, this preference for evolution over a static constant now stands between 2.8 and 4.2 sigma. This is not yet a 5 sigma discovery, but it is a highly significant signal that cannot be ignored. It represents the most direct challenge yet to the Standard Model's simplest form. This is precisely where the Fonooni Temporal Field Theory, or FTFT, enters the frame. Developed independently and prior to DESI's latest results, FTFT was built on a radical premise: that time itself is not a smooth backdrop, but has a quantum, granular structure. From this foundational idea, FTFT naturally predicts that what we call dark energy is not a constant lambda, but an emergent dynamic effect, a manifestation of the universe's evolving temporal field. Crucially, FTFT did not tweak its parameters to fit DESI's curve after the fact. Instead, it predicted the very qualitative behavior DESI now sees: a dark energy equation of state, W of Z, that evolves from a more negative, phantom value in the past towards a less negative value today. This evolution inherently leads to a profound cosmological shift, a transition from acceleration to a future phase of gentle deceleration. The quantitative alignment is striking. FTFT's predicted trajectory for W of Z falls almost exactly through the center of DESI's 1 sigma confidence band. It accounts for the suggested phantom crossing, where W dips below -1, and it pinpoints the transition redshift for deceleration around Z of 0.35, which aligns beautifully with the features in the DESI data. So, how do we move from this intriguing alignment to a robust test? The path is clear and collaborative. First, we must perform a direct statistical confrontation. This means taking the full FTFT model, with its specific parameters like the temporal field mass of approximately 152 GeV and its coupling strength, and running it through the same rigorous Markov chain Monte Carlo pipeline that the DESI collaboration uses. We will fit it directly against the public DESI BAO and growth of structure data. The key metrics will be the chi-squared fit and, more importantly, the Bayesian evidence. Does FTFT provide a more parsimonious explanation of the data than a simple phenomenological W0WA model? Second, we leverage DESI's unique multi-tracer capability. FTFT's temporal field could subtly affect how different types of galaxies, LRGs, ELGs, quasars, trace the underlying cosmos. By analyzing these tracers independently and together, we can search for unique signatures consistent with FTFT's non-local couplings. Finally, we look beyond cosmology to forge a unified test. FTFT's most dramatic prediction is not cosmological, but gravitational. The existence of correlated space-time glitches in the 30 to 100 Hz band of gravitational wave detectors, like LIGO. A joint analysis plan between DESI's large-scale structure maps and LIGO's 05 observing run could search for these signatures, turning this from a cosmological model into a theory of fundamental spacetime. In summary, DESI has opened a door by revealing the dynamic potential of dark energy. FTFT provides a specific, fundamental, and predictive key to walk through it. Our proposal is to take that key, crafted from quantum principles, and test it directly against the exquisite empirical lock built by DESI. The opportunity is to not just describe an anomaly, but to explain it from first principles. By demonstrating that a theory rooted in the quantization of time, via the boson, can accurately predict the complex dynamics of the late-time universe, FTFT is positioned as a leading candidate to replace the LCDM, or lambda-cold dark matter, paradigm, and offer a unified explanation for both the quantum and cosmological realms. DESI's evolving dark energy signal aligns remarkably with FTFT's predictions derived before the 2025 release. The temporal field mechanism offers a unified, non-fine-tuned explanation for cosmic acceleration, quantum gravity structure, and the resolution of Hubble tension. FTFT predicts continued weakening of dark energy, measurable in DESI Year 3 and Euclid lensing 2026. Combined with gravitational wave echoes, DESI may provide the first cosmological scale confirmation of quantized time. You can find additional information and data formulas on the Fonooni Temporal Field Theory webpage, or by reviewing the published paper in the Journal of Theoretical Physics and Mathematics Research, or refer to the ftft.world webpage for supplementary information and data formulas.